Greetings of the day, dear students. In this video, we are going to discuss about the EMF equation of a single phase transformer, and we will discuss about its equation and its derivation and the terminology used to derive that, and also we will discuss some examples how to find out the number of turns and EMF induced. All these things we will see in this video, right? So with respect to the EMF equation of a single phase transformer, you observe this diagram. Here V1 indicates the primary side applied voltage, E1 indicates capital E1 indicates primary side induced EMF, N1 indicates primary side number of turns, N2 is the secondary side number of turns, and E2 secondary side induced EMF, and B2 is the secondary side voltage across the load. So these are the important terminology, right? V1, E1, N1 with respect to the primary side, V2, N2 and E2 with respect to the secondary side, and phi indicates the flux linking both the coils. It's a maximum flux in the core, and F indicates the frequency of AC supply in H. Now if you observe the flux phi m, the maximum flux in the core, for every 1/4 cycle it is reaching the maximum value. It is reaching what? It is attaining the maximum value. For every 1/4 cycle you can observe it is reaching its maximum value. Now the question arises, how much voltage will be induced in the primary and secondary? And V1 is the applied voltage. How much voltage? It depends upon which factors we will see here. Here the flux in the core reaches its maximum value for every 1/4 cycle. Just now we have discussed. Okay, and average rate of change of flux for 1 second. How much is its there is a change for 1/4 cycle? It is changing. It is reaching its maximum value. And its average rate of change of flux is given by phi m divided by 1/4 F. So it is equal to 4F phi m Weber per second. This is the average value, right? So rate of change of flux per turn is the induced EMF. This is important. Rate of change of flux per turn is the induced EMF. So now how much amount of EMF is induced? That is simply equal to the 4F phi m. The units are volt. But if you observe, this is the average value. This is which value? Average value. With respect to the sinusoidal quantities, a quantity which is varying like this, okay, the form factor is given by its the ratio of RMS value and average value. And in the previous classes we have seen its derivation. The form factor of a sinusoidal quantity is given by 1.11. Now if somebody asks you what is its RMS value, it is simply average value into 1.11. Because we are interested to find out the RMS value. We want to find out the RMS value of the induced EMF. Moreover, observe this is the induced EMF per turn, for not entire turns, right? Yeah. Now RMS value is simply equal to the average value into 1.11. Clear? Now if you multiply 4F phi m with 1.11, we will get 4.44 F phi m is the induced EMF per turn. Now coming to the RMS value of the induced voltage for n number of turns. Total number of turns are, if it is primary, we have taken it as N1. If it is secondary, we have taken it as N2. Now, the total value will be equal to the induced EMF per turn into number of primary turns. Therefore, E1 equal to 4.44 F phi m into N1. But here, if you observe, maximum flux density Bm is given by maximum flux per unit area. So here, in the place of phi m, we can also write phi m equal to Bm, maximum flux density into area, right? So that is what we have done here. E1 equal to 4.44 F N1 Bm into A. This is very, very important. 4.44 F N1 B A. N1 is the number of turns in the primary side. F is the supply frequency in H. Bm maximum flux density A, area, right? Now similarly, for the same thing will be applicable for the secondary E2. E2, the RMS value of induced EMF for secondary is given by E2 equal to 4.44 F phi m into N2. In the place of phi m, you can write Bm, maximum flux density into area. So 4.44 F N2 Bm A. So these are the two equations which describes the induced EMF in the transformer. Induced EMF in the transformer, right? Yeah. Now let me see a small problem. A single phase 50H transformer of 500 by 100 volt has maximum core flux density of 1.5 Weber per meter square, effective cross-sectional area of 50 centimeter square, and determine N1 and N2. He gave you the frequency of the supply 50 Hz. Observe from the data given, we can observe the frequency is given 50 Hz. Primary side voltage V1 equal to 500 volt. Secondary voltage V2 equal to 100 volt. Maximum flux density Bm equal to 1.5 Weber per meter square, 1.5 Weber per meter square. Cross-sectional area. Dear students, please focus here. This is where the chance for to commit the mistake. The area is given in centimeter square. Please express it in meter square. So it is simply 50 into 10 power minus 4 meter square. Now from this we know the flux density, we know the cross-sectional area. Now we can find out phi m. So phi m equal to Bm into A. It will be equal to 1.5 into 50 into 10 power minus 4, and we get around 75 into 10 power minus 4 Weber. This is the maximum flux, right? Now just now we have derived the EMF equation. It is given by E1 equal to 4.44 F phi m into N1, right? So it is equal to E1, that implies we want number of turns. We want number of turns N1. N1 equal to E1 divided by 4.44 F phi m. E1 is already known, 500 volts. 500 divided by 4.44 into 50 into 75 into 10 power minus 4, and we will get that value as 300. If you get any fraction value, point something, you round up to the nearby integer, because you cannot have half turn, 1/4 turn like that. If you get something point something, you please round off to higher digit, right? N1 equal to 300 turns. Clear? Now what about N2? N2 will be E2 by 4.44 F phi m. E2 is given 100 whole divided by 4.44 into 50 into 75 into 10 power minus 4. we will get 60. N2 is 60. Clear? So in this example, simply he gave you primary voltage, secondary voltage, supply frequency and maximum flux density cross-sectional area is given. From that we have found out the number of turns in the primary and secondary. We have found out the number of turns in primary and secondary. In this entire discussion, this formula is important. E1 equal to 4.44 F 5M N1. Clear? Yeah, good. Now let me see one more example. A 100 kVA 3300 by 240 volt 50 H single phase transformer has 40 turns on secondary winding. Assuming an ideal transformer, calculate primary and secondary currents on full load. And the next one is maximum value of flux and number of primary turns. Maximum value of flux and number of primary turns. Observe, dear students, first write down the data given. It is a single phase transformer. Frequency of supply is 50 Hz. Clear? 3300 by 240. How do you understand this? Most of the problems, the data will be given like this only. 3300 by 240. Its meaning is, it's a primary voltage V1 will be 3300 and secondary voltage V2 is 240. He won't give you clearly that primary voltage V1 equal to secondary voltage V2 equal to. From this data given, we should understand this 3300 slash 240. Its meaning is primary voltage is 3300 and secondary voltage is 240. Now the rating of the transformer is also given. Rating, the power rating. And he told one more condition, ideal transformer, no losses are there, ideal transformer. Okay, whatever input is given and you will get it as an output. For example, input if you are giving V1 I1, at the output we will get V2 I2. Efficiency will be 100%. Right? Ideal transformer, no losses will be there. Clear? Yeah. Now V1 I1 equal to V2 I2 equal to 100 kVA. Dear students, please write in the place of K, kilo, 10 cube, 10 power 3. So it is simply 100 into 10 power 3 volt amperes. This is what the data given. So please don't be don't feel difficulty of doing the problems. First, from the problem itself, please write down the data given. Some clarity we will get. Some idea you will get. Then please write down what are the unknowns to be found out. And you just simply apply the related formulas with respect to that concept. Right? So here the primary turns N1 equal to how much? N2 he gave you. Has 40 turns on secondary winding. So secondary turns, the variable name is N2. N2 equal to 40. Clear? Now primary turns N1 equal to how much? Primary current drawn by the transformer. Primary current I1 equal to how much? I2 equal to how much? That is what we are asked to find out. Good? Yeah. Next, observe from the basics, V2 by V1 equal to N2 by N1 equal to K. This is very familiar. V2 by V1 equal to N2 by N1 equal to K. So here the value of K equal to V2 by V1. V2 is already known, 240 divided by 3300 and we will get 0.07272. And once you know the value of K, N1 equal to N1 will be how much? It is simply N2 by K. N1 equal to N2 by K. Why? Because N2 by N1 equal to K. Clear? N2 equal to 40 already given. K just now you have found out. Therefore, our N1 will be 550 turns. N1 is 550 turns. Primary turns is over. Now from the power rating, we are supposed to find out the values of these currents also. With respect to the current, I1 by I2 equal to K. I1 by I2 equal to K. Now the rating is given 100 kVA, that equal to 100 into 10 power 3 volt ampere. Just make it equal to V2 I2. V2 I2. So now if you want I2, this power rating divided by, this is power rating divided by voltage. This power divided by voltage, if you take, we will get the current. Power is already known. Secondary side voltage 240. So I2 will be how much? The secondary side current is 416.66 amps. Clear? Now we want to find out I1, primary side current. What is the primary side current? Relation between primary current and secondary current. I1 equal to I2 into K. I1 equal to I2 into K. So 416.66 into 0.07272, we will get 30.3 amperes. Clear? Yeah. Now what will be the voltage induced? E1 equal to, this is one more basic. To solve this entire problem, two important basics we have used. If you know those two formulas, then only we can solve the problem. One is E1 equal to 4.44 Fn phi m. Now he is asking what is the maximum flux density, phi m. It is simply E divided by 4.44 F into N1. Clear? Yeah. So 3300 divided by 4.44 into 50 into, just now we have found find N1 550. So we will get 0.02702 Weber. Better express it in milliweber. Express it in milliweber, right? So therefore phi m equal to 27.02 milliweber. So these are all what the things we have found out. N1 equal to 550, I1 equal to 30.3 amps, I2 equal to 416.66 amps, phi m equal to 27.02 milliweber. Dear student, observe this, all these things we have drawn in the form of a diagram. V1 3300, so V1 is 3300. The current flowing through the primary N1 550, N2 40 turns. Current flowing through the primary 30.3 amps. Current flowing in the secondary I2 416.66 amps. And the voltage V2, secondary side voltage V2 240 volt. And the flux linking both the coils, maximum flux density 27.02 milliweber. So this is what we have done in this problem. So what I want to say is, dear students, the moment you look the problem, don't think that for the final answer itself you will get the full marks. By doing all these steps, easily you can get some marks will be awarded. Don't think always if you get the entire final answer only, they will marks will be allotted for the procedure. You have to write the data given like this. Don't forget to specify the units. For this step itself, you may get some marks. And you write the formulas related to solve this problem. Do some substitutions. Don't directly show the answer, even though you have calculated this calculation in the rough side or back side of your booklet, but please show the substitutions in your booklet. It gives some impression for the paper evaluator, right? Yeah. For example, something like this here. In the place of V2 by V1, if you do this entire calculation in your booklet or rough side, and if you directly show the answer like this, V2 by V1, it will not add that much, right? You do the substitutions. Show the substitution 240 by 3300. Then you write the answer like this. The presentation skills count. And similarly, wherever formulas comes, first write down the formulas, do the substitutions, then final answer. Answers, don't forget to write the units. These small tips will help you to score more marks while attempting the question in end exam. Okay, students, thank you.